slides are visible to you. So, good evening everyone. I am Karthik Yadav, currently Prime Minister Research Fellow in the Department of Water Resources Development and Management, Indian Institute of Technology, UP. Uh, so, I welcome you all on this week number 12 and lecture on irrigation and drainage. So, this course is basically designed by Professor Ludhiana and he's from Agricultural and Food Engineering Department, Indian Institute of Technology, Kharagpur. Yeah, I'm Prime Minister Research Fellow and PTL teaching assistant. If you have any query related to this course, whatever, so we are at the last lecture of this overall course, and till now, whatever I've covered, in general, if you have any query related to this subject, you can directly write down to this email ID. So I will try to return your queries within 24 hours. And also, whatever content, like up to week number 11, whatever covered that I have already uploaded in this YouTube channel. So either you just click on this link or you can also scan this QR code. Also, I'm uploading all the lecture materials that I have prepared this Google Drive format. So apart from this irrigation and drainage engineering course, I have also covered in last semester, that is soil science and technology course, and also like micro irrigation engineering. So both are very helpful for you, right? For like preparation of any examination like junior research fellowship, senior research fellowship, or national eligibility test conducted by ASRP, or like other like gate also. Okay, so before we moving, so let me quickly recap like what we are doing. So like in this week basically we'll focus on drainage case studies. So like I'll not go in detail, but like we'll just quickly recap like what kind of content we have already uh, talked during last week. And then and drain model. So it is like conceptual and fundamental model that are widely used in this drainage design. Then we'll look over at irrigation efficiency. So this is also very important. So this we have not discussed in detail earlier. So in this last week we have discussed this in detail and certain aspects of irrigation economics. And finally we have see that how properly we can use irrigation planning and management. So yeah, though its lecture is like for that supposed to be delivered on tomorrow at 11 October, but like due to certain unavoidable circumstances, I am taking this in this lecture today. So sorry for that, but like I hope this will be beneficial for you. Yeah, so let me quickly revise what we have covered last week. So in last week we have focused on irrigation, like drainage design aspects. So in that, first we have started with like what kind of runoff we are expecting on our fields. So for that, various methods are available, and one of them are like three major methods. We have looked over it, and like rational method, Cook's method, and soil conservation service economy method. So among this, like this basically this discharge estimation is most essential for hydrologic design aspect. So once you have your design discharge, then you can go with the other aspects of like uh, permissible velocity, and then you can say about hydraulic design like channel width, channel depth, then maybe you can say like what kind of material there you need to put. All that hydraulic aspects also depends on this hydrologic aspect. So we quickly look over these aspects, and we understood that okay, what are the limitation of this three method, and which one is like we need to use where. So we identified that SCSC and cow number method is the most most accurate among these three and also more detailed one. While a rational method is empirical formula or more like a black box in nature. So, but yeah, it's still providing required discharge. That is an approximation, but we still use the discharge if we do not have this kind of detailed parameter. Then we understood runoff coefficient and everything. Then uh, start in continuation in this. We focused on drainage and surface drainage system design too. That's more focus on first aspect, the estimation of discharge that we already talked three method. Then we need to decide the grade, so that is longitudinal slope of the ditch, and finally cross section of the ditch. Then, so this is like for conventional drainage design aspects, and then for non-conventional drainage design methods, so we have a few methods like vertical drainage, bio drainage, or like there's a mold drainage, tile drainage. So not tile drainage, but mold drain. Yeah, so these are the non-conventional method because traditional subsurface drainage system have a limitation, particularly that it can maximum drawdown depth that can do is about 2 meters. But in case of non-conventional system like vertical drainage, we are aiming to remove excess water beyond its limitation. So it can go maybe up to 10 meter, 15 meter, depending on the uh, 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 depending on the what kind of plant we are using. Okay, so basically in vertical drainage, so or plant, or you can say what we are doing, we are installing certain tube wells so that pump out the groundwater, and its advantage that it can lower the water table from much greater depths. It should be around like 20 to 30 meters. So uh, while in case of the conventional drainage system, it is around 2 meters. So area around tube well remains available for crop production. So so there is a less problem of waterlogging, but main issue with this is like we required energy source to extract huge amount of water. Okay. While then we also have bio drainage. So bio drainage is like pumping of excess soil water by deep rooted plants using bioenergy, and plants meet their transpiration demand by directly withdrawing groundwater. So this is just quick overview. So this is vertical drainage, this is bio drainage. Then we have also looked over at the mold drainage. So mold drainage is basically where we are doing this. So whenever your soil having more than 35% of clay and less than 30% of sand, so that ensures the mold drainage remains stable, and it performs more better as compared to other part. And like it should be, we are generally designing this mold drainage for short term drainage needs, and like it often around 3 to 10 years. And uh, land having a grade in this mold drainage system is around 0.4 to 4%, and ideally it should be 3%. And waterlogged areas where pipe drains are uneconomical, so it have more cost. In that case, also we are going more with mold drainage. So yeah, obviously it's have a low cost alternative to subsurface pipe drainage, and it improves productivity in clay soil. Also effective for 3 to 10 years depending on the site condition. Then we have also look over at the other aspects, economic aspects of the drainage system. So that we have discussed about annuity payment, inflation factor, non NPV, and best benefit to cost ratio. Now, in week number 12, basically we have focused on certain case studies, and then we have discussed about end drain model. Then we have irrigation efficiency. So we have already looked over it in briefly during week number 2 or week number 3. But in this lecture, basically we focused on more detail. So basically, so there is a case study of Punjab Agricultural University farm that we have looked over it, and that have a located in low-lying area, and area of that. Study area is around 30 hectare. Just a second. So area we have looked over it is like 30 hectare, and that suffers from waterlogging and soil salinity, right? Both issue because you know that most of the northern India that have a higher groundwater level, as well as there is also problem of salinity due to over application of fertilizer or salt present in the soil as well. So there is accumulation of runoff and seepage from surrounding higher areas. Then there is absence of proper surface and subsurface drainage facility. So maintaining favorable soil balance is crucial for sustaining irrigated agriculture in this region. So also the groundwater level, groundwater table, that is was around very close to surface, and that it is reported is around 0.3 to 1.5 meter below ground level in several plots, that causing acute salinity as well as poor crop productivity. So basically, like objective of this case study is to develop a design criteria for surface and subsurface drainage system and land reclamation of affected area. Then second one is to establish suitable investigation technique to identify source of waterlogging and salinity, and finally to formulate management procedure for reclamation and long-term sustainability. First thing, that authors did is that they did reconnaissance and field survey. So in that they have collected multiple data sets that affect the drainage aspect. So first is like what are the rainfall pattern, what kind of soil they have, then what kind of cropping pattern or existing land use classes in that within that plot. So they have just estimated okay what kind of design discharge they're expecting, and they have checked with the based on that design discharge. So which kind of method is best suitable for that? So that all that they have checked, and that like earlier methods, so they are doing is biological control and pond drainage were tried out but failed to meet technical or economical standard. But in this, basically after this detailed study, they have adopted new approach. So that is gravity drainage connected to the Ludhiana light, like so this is like a more regional context. So what they did just this gravity drainage. So they've connected this low-lying area with the gravity flow, and they just connected that with the 2.4 meter above its water surface to ensure natural outflow. Then they also discuss about like topographic survey in this farm and delineated of drainage area, establishing grade and located field drains. Then they also installed certain piezometers on 60-meter grid at depth of 1.5 to and 2.5 meter to observe fluctuation, and observation wells are 1 meter, 1.5 meter depth help monitor shallow water table behavior. Then there were different kind of aspects. I'm not going into the detail. So they finally designed the drainage system based on the topographic routed data, and combined surface and subsurface gravity drainage system was recommended, and it components include like interceptor drain. So interceptor you drain, you know that like it is collecting the if the flow is like uh, in this direction, so you are intercepting this flow with having a certain drainage concentration perpendicular to the flow direction, right? Then relief drain, so along the middle section to collect the surface runoff and shallow groundwater level, so they also have a relief drain, and then outlet drain, so to discharge into the Buddha Nala. So it's basically collecting this drainage water and discharging in this local Buddha Nala, to ensuring safe movement of drainage flow. Now, after implementing this system, they observed that system is successfully lowered the groundwater table and reclaimed the saline soil. It also enhanced the drainage efficiency and soil productivity, and it's not observed like weekly, but after 2 to 5 years, it might take certain times to get this kind of benefits, and that this design successfully demonstrated the how site-specific investigation and design criteria can solve the persistent waterlogging in alluvial plains. So key learning from this is like integrated surface and subsurface design yields better performance than a single component system. So it's always better or always recommended to go with the uh, more detailed analysis and like maximum data collect during your initial or recurrence survey. Then instead of going with the one solution, it is always good to have a multiple solution in mind and and among that just not only fit one, try multiple scenarios and whatever fits better according to the condition. So install that particular structure or drainage system there. Then also it's also not installing this kind of drainage system uh, after your survey and initial design. It's not a good idea to just stop and just see what is happening. You have to monitor continuous everything that is related to drainage. Like so, for example, you need to monitor your piezometer through. You need to monitor the outer level. Then you also need to monitor salinity. You also need to monitor other hydrological aspects. So because this all impact the waterlogging issue, right? So if you found any consideration that is like above the limit, in that case you slightly modify your design or just add certain aspects to that so that can add up with the certain extent condition. Then gravity drainage system. So it is like a cost-effective system that in this study they have basically installed, and that is slightly elevated in areas with reliable outlets. And this we have summarized that first one, that case study lecture, and then we have moved towards the drainage model. So drainage models are powerful tools for analyzing, designing, and optimizing the land drainage system. So there are n number of models that help us to simulate the hydrological, hydraulic, and salinity condition to make the data-driven decision for reclamation of uh, affected soil. So main objective of drainage models is to predict the water table behavior in the different drainage layouts and recharge conditions. And we know that there are multiple conditions like steady state, unsteady state, and in that also there were different aspects of like fluctuating water table or like there is sudden drop in water table, sudden rise of water table. There are multiple situations. So in that condition, this kind of drainage model help us to predict the water table behavior. And then also we can design the optimal drain spacing and depth for desired water table control. Third one is to assess the salinity and leaching behavior in the irrigated and waterlogged soil. And finally, we can also evaluate the long-term reclamation strategy and to reduce the field experimentation caused by simulating alternative scenario digitally. Right. So there is not only one aspects of using drainage models. So there are multiple aspects. So we can use drainage models so like just before starting of our installation or field experiments. So we know that installing drainage system at field that involves huge cost. So doing drainage system installation just for one scenario best case. So instead of that, just go with the multiple scenario run and check what is coming out in different condition. Then among that, choose the best scenario and then only perform experiment for that condition. Then also you can based on the collected data from installed system, you can evaluate the long-term reclamation strategy. So that is including climate condition like future climatic changes. So that will help us to build the sustainable management of soil and water resources. And you can also assess the salinity and leaching behavior. Right? Suppose you have designed something and that in that scenario, how leaching and salinity will be reduce. And of course, you play with the design diameter, drain depth, and then certain filter media around the drains. So all these are changing aspects, and you can easily uh, interpret or just get quick output by using this kind of model. So one of that model is the end-drain model, and end-drain model, its full form is energy drainage model, right? Energy drainage model. This is an analytical and computational tool used for reclamation, or you can say remediation, rehabilitation, and or restoration of the saline or waterlogged soil. Extends the traditional drainage theory by incorporating energy balance principle along with the Darcy's law and water balance equations. So these are the overview of and drain model. So there is energy drainage model. So it have a different aspects like intro, then you figure, then you input, output, and graphics. So you can see this in figure how you can you are representing the drainage system, right? So this depth you can modify, then this water table you can modify, in particular layer depth you can modify, then you have a different anisotropy that you have to modify, right? So all these aspects you can modify and develop your own model. So conceptual basis is like con- conventional drainage models like Hugout or lower dam that are mainly rely on the Darcy's law and steady state water table balance, while end drains that advances this by integrating energy balance, accounting for both hydraulic head and energy dissipation in layers. And this allows for more realistic situation of subsurface flow and solid movement in heterogeneous field balance. So this is like more advanced one, and its key feature side is like it have a multi-layer soil representation. So it works wells and allow up to three soil layers with different hydraulic properties. And bottom two layers can have a distinct horizontal hydraulic conductivity and vertical hydraulic conductivity. It also integrate the Darcy's and analytical framework to ensure the compatibility with the flow hydraulic and energy dissipation. And it also accurately predicts the flow rates, potential gradients, and drain discharge. Also, it is flexible in application, so it can be useful in both subsurface drainage design in saline clay or heterogeneous soil. And also, it's specially applied in condition that we have in the Punjab, Haryana, and other regions of the saline soil. However, there are certain model assumptions because you have to remember that no model are accurate. Just all models are just simplified version of the reality. You must have to take in mind during if you are doing modeling. Okay, and no model provides accurate results. So that's why you have to do multiple scenario, and among that you need to choose one or two for like implementation, and during implementation also you will observe certain different behavior as compared to what you have predicted. Okay, so that's why it is always great to having idea about okay what kind of assumption you have before you are going for modeling. Okay, so that will help us to understand okay what you are missing and what you are not predicting. So due to that, so it is important to understand the model assumption of Android model. So there are basically four assumptions. So first one is a steady state fluxes. So like there is a no storage of water or energy within model. Then vertical 2D flow. So flow pattern repeats in a parallel vertical planes in and drain. Then uniform horizontal flow. So constant horizontal component in cross section, and final one is specially constant K. So hydraulic conductivity does not vary laterally with layer. So these are the assumption of this model. So steady state flux is it says there is a no storage of water or no or no energy exchange. Okay, or no energy storage. Then vertical 2D flow. So flow pattern repeats in a parallel vertical planes in 2D direction, and uniform horizontal flow. So constant horizontal component cross section. So whatever soil layer you have defined, there is also always constant horizontal component across the flow section, and especially constant K. So hydraulic conductivity does not vary laterally within layer. Okay. So once you have defined your layer with the different properties, so there is much no much change in the layer. So, but in reality, this condition might not get satisfied. So there is always difference in results. Okay. So that's why, but always having this kind of model that is really helpful at initial stage, right? As compared to having no idea or putting just your money randomly. So Android model structure. So it have five tabs. So first one is intro. So intro defines project title, user, and description of the problem set. Then you have figure. So that displays the schematic representation of the drainage system, soil layers as well as flow lines. Then you have input. So in input, we are generally providing field data such as hydraulic conductivity and different layers, and drain depth, drainage spacing, recharge rate, and other boundary condition like how surrounding condition are reacts with this drainage system. Then in output, we are generally having a result that compute the drain discharge, water table profile, and energy balance outputs. And finally, we can visualize using graphic tabs. So it displays plots of flow rates, potential line, heat distribution, and visualization of interpretation. Then its practical utility is like it applied for design and performance simulation of drainage system in a saline or waterlogged zone. It's also useful in developing reclamation plans where field data are limited. Yes, it's quite obvious that we can use for multiple scenario and then develop certain useful scenario that we can further study at the field, field level, and it also enables the assessment of energy loss, drain discharge efficiency, and layer-wise flow contribution. Now, its example application are like reclamation of saline soil in a PU farm, Ludhiana. So, in that, we can use this kind of model that we can using this to optimize the drainage spacing, drainage depth for different conditions, and also helps to validate the field measure data within model simulated state condition. So in summary, like Android models bridge gaps between the field-based drainage system with the theoretical hydroelectric analysis. It is ideal for fundamental research and like teaching purposes. For field design of subsurface drainage system, also we can use this, and policy level evaluation. So that also get benefited arid and semi-arid regions where there is a problem of salinity, waterlogging issues. Now, following that, in third lecture, we have focused on the irrigation efficiency. So, irrigation efficiency refers to the effectiveness with which irrigation water is conveyed, applied, stored, and utilized by crops. And generally, it helps engineers and farmers to evaluate how much of water delivered from source like canal, reservoir, or pump and is actually beneficially used by plants versus lost through leakage, evaporation, runoff, and depopulation. Yeah, this is quite like definition, but let me tell you in a so in general, like in simple term, if I say we can say that whatever water we are extracting from any source, suppose canal network, okay. So what we are doing, we are diverting this canal water to farm, right? So in between there are lots of losses, conveyance losses, storage losses, or there is not always that whatever amount we are providing to crop that are that are they are using for their transpiration or food production purpose. There are in each stage there is a losses that is related to leakage. Okay, leakage through pipe, leakage or losses through evaporation, losses through runoff, then losses through deep percolation that are ultimately going towards ground recharge. So all of each stage have a different aspect. So it is very crucial to understand this irrigation efficiency. Its objective is to minimize the water losses and maximize the fraction of supplied water that contributes to the crop yield transformation. Now, first come is water conveyance efficiency. So it indicates how efficiently water is transported from water source, that is like canal or any well or pump, to the field. So it's generally ratio of water delivered to the field divided by water that we have extracted from source or diverted from the source. And in this case, whatever water we have diverted from the source like canal or any tube well or pump, all this water are not available at field. Okay, so where it is going? So there are always certain losses through seepage, unlined canal if your canal is unlined. Even if you have line canals, over the time there is a development of cracks, and that there is a loss of water through seepage. Then water losses from evaporation to the canal surface, as you have this canal is open, so there is always chance that this water is lost to evaporation, and also there is like leakage and poor maintenance issue. So practically, it's only 60 to 90% of the water what we have diverted from the source, it reaches to the field. That also depends on the what kind of source water we are using. Also like canal lining or pipe network that we have, and certain maintenance aspects. Then second efficiency is the water application efficiency. So once we have water at our farm, then we are measuring how much of water delivered to the field and is actually stored to the roots. It is basically ratio of what amount of water delivered to the field. So, right. So this amount reached to the field that will come down, and what amount of water that is stored in root zone. The ratio of this both two is known as application efficiency. And typically, we know that during application, there is loss through runoff as well as depopulation, right? Also, there is a loss of through evaporation in this case also. So it ranges between 40 to 60%. And for example, for different irrigation system, like drip irrigation system have highest uh, water application efficiency as compared to sprinkler and surface water, furrow irrigation or check basin irrigation. Why it is like that? Because you know that whenever you are applying water through drip irrigation system, you are applying it through pipe network. Okay, so you reduce the loss of evaporation and depopulation. Then also you are applying water at the near crop root zone. Okay, you are not applying water throughout the field like uh, like we are doing in a furrow irrigation, water irrigation, or basin irrigation. In that case, you have a higher loss through evaporation as well as depopulation, or there is also like a runoff. But in case of drip, you have less or comparatively lower losses, and in sprinkler you might have losses as you are sprinkling the water in surrounding soil. but still it is comparatively low as compared to other surface flow irrigation methods. Next to that, we have a soil water storage efficiency. How effectively the required soil moisture deficit is replenished by irrigation. So it is generally ratio of water stored in root zone divided water needed to bring soil to the field capacity. So higher the soil water storage efficiencies, it means the soil moisture restored efficiently. And if you have a lower soil water storage efficiency, it means uneven infiltration and inadequate wetting pattern. Next to that, we have irrigation efficiency. So it combines both conveyance and application efficiency, showing the overall effectiveness from the source to the crop root zone. And just multiplying conveyance and application efficiency, you have the overall irrigation efficiency, or you can say irrigation efficiency. Then overall irrigation efficiency, so it represents the total irrigation system performance, including state diversion, conveyance, and application and storage. So it's combined all. So conveyance, application, and storage efficiency. So by combining all this, it represents the overall irrigation efficiency. So there is a difference between overall irrigation efficiency and irrigation efficiency. So the difference is just only by consideration of soil water. Soil water storage efficiency is, suppose you have a soil, right? So that soil have a certain field capacity, and field capacity it means you know that maximum water that can be stored uh, uh, without gravity drainage loss. So, or on other words, you can say that whatever water that soil can hold against the gravity, so that is its field capacity. So water stored in the root zone divided water needed to bring to the field capacity. So that is your water storage efficiency. And if you multiply that with the conveyance and application efficiency, you will get the overall irrigation efficiency. Then your effective irrigation efficiency, so it takes into the account of some losses like deep percolation that still be beneficial if they recharge groundwater and for later reuse, and it used in a basin level water accounting where return flows and groundwater recharge are considered beneficial. So effective is given by like beneficial use like ET plus reuse divided by total diverted water. And there is also concept of irrigation uniformity because by just defining irrigation efficiency that alone not represent the overall goal of efficient use of water, but you also need to check irrigation uniformity and crop response. So even if water is applied efficiently, non-uniform distribution can cause problem related to the over irrigation in some area and under irrigation in certain area. That cause the waterlogging, salinity as well as crop stress, and that it directly impact the crop. Therefore, uniformity and ensuring even water application throughout our field that will help us to optimize the yield and maximum water productivity. So these are the efficiency type and its typical range. So we know that conveyance efficiency, so that its typical values ranges around 60 to 90%. And its major influencing factor in case of conveyance efficiencies, canal lining, and seepage losses. Also, there might be some leakage from networks. Then application efficiency, so it is around like 40 to 80%, and among that, like it totally depends on which kind of irrigation method we are using and what are the field level or leveling and surveying we carried out before choosing irrigation method. Then we have a soil water storage efficiency, so its range is around 70 to 95%, and it major influencing factor is infiltration uniformity. Then we have irrigation efficiency. So it again like multiplication of conveyance and application efficiency. Then we have overall efficiency of irrigation, that is um, like multiplication of conveyance, application, and storage efficiency, and its ranges around 35 to 65%. And effective efficiency, that is include groundwater reuse also, so it is around like 50 to 80%. Next, as uniformity is important, so we have also looked over it and defined the Christensen uniformity coefficient. So it is given by 101 minus summation of xi minus x. So this is just like observed depth, and this is average depth. And if you have n number of observations, so just multiply with the average depth of the water that caught. So that will give you a Christensen uniformity coefficient, and it's typical ranges around like you can say if your value of uniformity coefficient is greater than 85%, so that is your best condition. But if it is less than 70%, it means you have poor uniformity. Then also, yeah, like after that you have a crop response to irrigation. So you know that even if water is uniformly applied, crop response depends on how efficiently plants use that water. For that, we have different kind of efficiency. So first one is a crop water use efficiency, or you generally also say water use efficiency. So to check that, like how crop is responding to applied water, applied amount of water. For that purpose we are using. So it's generally ratio of yield that we have derived divided by total water that is lost to evapotranspiration. So higher the water use efficiency means crop produce more yield per water consumed, right? Then second one that we have is irrigation water use efficiency. It is generally ratio of yield, crop yield divided by total irrigation water that we have applied. So it helps to evaluate the irrigation management practices and scheduling effectiveness. It also considers only irrigation component, not a rainfall. Okay. Finally, you have a overall water use efficiency. So that is like you can also say EWP or water use efficiency. That is given by like yield divided by effective rainfall plus evapotranspiration. So it represents the total water productivity combining rainfall and irrigation. Okay. So effective rainfall, that is you can just define as like whatever amount of rainfall that are useful for plant plant use. Okay, or plant benefits, production of food. So that is your effective precipitation, and that will help you to get overall efficiency of the system, right? So in this key takeaways, or like before we go, so see this, these are the water use efficiency metrics. So first one is the water use efficiency. So that is yield per evapotranspiration. So it governs like physiological water use. Then you have irrigation water use efficiency. So that is yield per irrigation applied. So that provides a field management aspects. And water is efficiency in total. So that will like give us yield per total water used. So that is more beneficial for basin and watershed analysis. Now, key takeaway from this irrigation efficiency lecture is like uniformity ensures the equal water distribution and critical for irrigation scheduling and design. And efficiency ensures water is effectively used for crop, and together they determine field performance, energy use, and crop stability. Also, you can see that starting from water source, what we did, like we are diverting this water to agricultural farm. Then this farm, like there are certain losses during transform this water to the field. In field also, the water is lost during application, depending on the what kind of irrigation methods we are looking or taking consideration, take into the consideration. Then we have uh, like uh, storage, you can say application efficiency, then your storage efficiency, then your overall irrigation efficiency. So this whatever efficiency we are looking over it. So by just getting this number, suppose you are getting 90% efficient water application, okay, but this alone not represent what is happening, okay. So because it is not telling about uniformity of water application throughout the field. So to check that, we required or we need to understand the uniformity coefficient and how uniformly we are applying water. And even if you are applying uniform water, the crop response to crop response to water application, that is not similar, okay, in entire field. So that depends on various aspects. So due to that, we have also defined water is efficiency, irrigation water is efficiency, as well as water is efficiency. So all there were different aspects. Suppose first one is like water is efficiency, so that defined as yield per what evapotranspiration. So it is it deals with, or it just provide us physiological water use, while irrigation water is efficiency, so that provide yield per irrigation. So that will help us to like field management aspects, like changing in field management practices of irrigation. And finally, at overall water is efficiency, that will help us to basin and watershed level analysis. Then we have after that we have focused on basic of irrigation economics. So as you know that irrigation economics deals with the economic evaluation of irrigation projects, cost benefit analysis, and optimization of water use for maximum crop productivity and profitability. Its objectives are to ensure the financial viability of irrigation project, to determine the optimal allocation of limited water resources, because you know that there is always like water is the uh, per capita water availability is reducing and declining, and also water distribution in entire world is not same, because there is a no source of water. So considering all this and determine this aspect, so irrigation economics help us to optimize this allocation of limited water resources, choosing selection of the optimal irrigation technologies, like more advanced technology like drip or sprinkler, or you can just continue with the surface water irrigation system. And finally, to evaluate the economic feasibility using net present value, benefit cost ratio, and IRR. So first one is the cost to benefit analysis. So that's also CBA, or you can say benefit cost analysis or ratio. So this is the foundation of irrigation economics in comparison between total project cost and total benefits over its lives. So benefit to cost ratio is just the ratio of present worth of benefits divided with present worth of cost. So if your benefit to cost ratio is greater than 1, it means this project is economically feasible, and if it is less than 1, then this project is not recommended. Then net present value, so it measures the project profitability in the monetary terms, and IRR, that is internal rate of return, so it discount rate at which net present value is 0. Then there are certain category that we need to understand uh, before the calculation of irrigation economics. So first is the capital cost. So we know that it is a one-time cost, and this also known as the investment cost. And its example are like just establishing structures like canals, you need to purchase any pumps, installation of pumps, first time. Then you have a construction of wells or tube wells in general, or putting money on purchasing pipelines. So this all come under initial cost because this is a one-time cost, right? It, we are not changing for long time. Then you have operational and maintenance cost. So this is recurring or annual expenses. So it is like involves electricity charges because that is you need to pay multiple times during entire project. Then your labor costs, your repairing costs, then your cost like replacement cost. That is a periodic reinvestment. So like pump or motor replacement because you know that this kind of certain electronic items have a limited lifespan. So that that is like important to consider. Then your benefits, so economic and social returns. So like you have benefits in terms of increasing in yield, reducing soil salinity. You have improved better environment or ecosystem surrounding your region. So that overall helping you to getting sustainable development. Then engineering economic analysis. So to convert the future cost and benefits to the present equivalent values using discounting principles. So in that you have a time value for money, then you present work method, annual equipment method, benefit cost ratio method, internal rate of return method. So all these are very important that you have looked over it. And also we have uh, checked about or talked about cash flow diagram. So it's generally used to visualize all project inflow, benefits, and outflow costs over the time. So it is just graph that shows that uh, inflow, so that is your all the benefits, and outflow, that is going out, that is your cost. So whatever cost you have invested and how it is how beneficial it is. So it is like certain diagram like this. And on horizontal axis, generally you have time years of the project life. In verticals arrows, you have upward benefits, and downward you have a cost. It helps to simplify the non-performing net present value and benefit to cost ratio calculation. Also help to visualize the loan repayment and operational maintenance cycles. Then we've also talked on transferring crop water production function from one climatic zone to another, and it helps to describe the relationship between the crop yield and water use, and why we need to use this crop water production function, because like it is like region specific and developed in the control experiment in one time climatic zone. We can also apply this in another zone, and before that we must normalize or transfer the function by testing climate climatic parameter like temperature, humidity, solar radiation, then management practices of that particular region, soil properties and fertility, and crop variety. Considering all this, by following these steps, transferring this groundwater production function from one climatic to another climatic zone, so that includes the normalization of the groundwater production function. So it expresses as a yield and ET as a dimensionless ratio. Then we need to adjust our climatic coefficient. So scale by ET naught or water product index, that we need to consider because each region have a different frequency of the transpiration rate because they have a different soil type, crop type, and uh, other physical properties of the plant and soil. Then we need to calibrate KY factor so that we estimate K using KY using local field and uh, field data, then validate the model, and finally applying for planning. So use the adjusted crop water production function for irrigation scheduling, efficient irrigation, and economic optimization. So like overall, so this is just overall concept of this what we have talked. And key takeaway from this is like irrigation economics integrates engineering, agronomy, and finance. And crop water production function transfer allows extending research based on function to new climatic region. And engineering economic analysis provides framework for evaluating long-term feasibility. And next to that, we have looked over it the crop wet. So this crop wet model, it is like a very fundamental and basic model that are we are generally or widely used model that is developed by Food and Agriculture Organization for planning, management, and optimization of irrigation water use. It uses climatic data, crop data, and soil data to calculate the crop water requirement, generate irrigation schedules, and scheme for water supply for different cropping patterns. Data input modules. So this program generally requires several types of input data to perform the reliable irrigation and water requirement calculation. So what this crop water is generally doing, so we are providing certain data sets like climatic. So first we have climate module and runoff module. So in that we are defining every data that is required to measure the ET naught. Okay. So this data is in the data include temperature, humidity, wind speed, and sunshine hour. If CT naught is not data is not available, so Cropwet can compute CT naught using this Penman-Montet equation. And again, if you provided this input parameter, it's all required by Penman-Montet equation. Then you have a rain module. So rain module that generally used to provide the rainfall data and compute the effective rainfall. So that effective rainfall is generally portion available to in that you have different method like fixed percentage method, USDA soil conservation service method, and other methods. So after this climate rain module, we have a crop module. So crop module is just provide the crop parameters and planning dates, and each crop type has specific values of crop coefficient, growth stage, then the initial development being the late stage, then length of each stage, rooting depth, depletion function, and crop coefficient curve, which help us to decide basis for ET calculation. Then you have a soil module. So soil module contains soil parameter and it's essential for irrigation scheduling input. So that include your maximum soil moisture content, field capacity, melting point, readily available water, maximum filtration rate, soil water holding capacity, infiltration behavior, and irrigation time. So all this will depends on this parameter. Then you have crop pattern module, so that allows input of crop pattern for a scheme water supply planning and useful for calculating total water demand of an irrigation command area. Finally, your calculation module. So by inputting all this detailed information that required for calculation, CropWet performs different analytical components to its main calculation module. So in that you have a crop water requirement module that considers the effective rainfall and gives the net irrigation requirement. Generally, net irrigation requirement is equal to crop transpiration minus effective rainfall. So that is so it basically means that whatever rainfall you are receiving, suppose and whatever crop water requirement you have, so that difference provides you net irrigation requirement. Suppose your effective rainfall in this area is around like 500 mm. Okay. And effective rainfall means this is water that is available after all the losses from depopulation, runoff, okay, and other losses like evaporation. This water 500 ml is available for crop use. Well, and if you are growing crops like sugarcane, rice, okay, that required much water than this. So whatever evapotranspiration will happen, crop evapotranspiration from sugarcane or rice, that is much far better than this 500. It means you need to supply that requirement of this crop by providing extra irrigation through certain irrigation methods. So that is your known as net irrigation requirement, so that produce monthly or seasonal water requirement summaries. Then you have a schedule module, so that calculate the irrigation scheduling based on soil water balance and crop stage. And basically, it helps us to decide when to irrigate. It means irrigation interval and how much. So that is your depth or finally, you have a scheme module. So scheme module performs the scheme water supply calculation given dropping pattern, and that is useful for canal command area plan assessing total seasonal demand and water distribution. Finally, it will generate the reports for gross irrigation requirement and net supply. So overall, crop model provides a complete framework for irrigation water management by taking multiple climatic as well as hydrogeological properties, and it is widely used by Food and Agriculture Organization (ICR), that is Indian Council on Agriculture Research, and Irrigation Agency to optimizing water use under different climatic and soil conditions. So, yeah, with this summary of this week number 12 is over. So let's take a 5 to 10 minutes break, and yeah, if you have any query, you can just ask right now or just write down in the chat box. We can discuss that, and yeah, so uh, let's have a break for 5 to 10 minutes. Right. That question number one. What is the main purpose of using drainage model like end drain reclamation study? So there are various options given. So we know that end drain model is used for reclamation of saline and waterlogged soil through subsurface drainage design, and it incorporates Darcy's law, water balance, and energy balance equations, where it flow through multiple soil layers with different conductivity. It assumes steady state 2D vertical flow, making it ideal for designing drainage spacing and depth in reclamation projects. And in general, like we know that it is steady state subsurface drainage system with layer soil inclusion, and it also beneficial for reclamation analysis. So, correct answer for this is option C. Evaluate the subsurface drainage and solid movement under steady state condition. Question 2. Question number 2. So, in a vertical drainage system, water table is lowered by primarily by. So, we know that in vertical drainage system, we are installing multiple tube wells. The tube wells are in that from we are extracting water, so that is like from deeper depth as compared to conventional drainage system. So that will major benefits, and its concept is like in area with low hydraulic conductivity and deep impermeable layers, vertical drainage is often more effective than surface and subsurface drainage. So correct answer to this is pumping through tube wells where we are extracting water from impermeable and low hydraulic conductivity area. Option C is correct. Question number 3. Which of the following is an important assumption of drain model analysis? So this is the figure of drain model. So there are multiple modules within this. You know that, right? And this so we define various. Mainly, it allows us to define three soil layers that having a and particularly this lower two layers that we can define horizontal as a material hydraulic conductivity. Then you can define depth of impermeable layer, depth of water table, then design diameter of the drain pipe, depth of installation, everything. And this basically we are main assumption or important assumption is like whatever simulation we are doing, that is in a steady state condition. It means there is a no storage even of water or energy. And also like there is a flow that is a vertical and it is of a two dimension, not three dimension. Meaning water flow pattern repeats in a parallel vertical planes. It simplifies the computation while retaining the accuracy needed for designing rate, spacing, and estimating discharge. And in real world, transient variation that are neglected, which is acceptable for long-term average recognition. Correct answer is for like steady state two-dimensional vertical flow condition exists. That is the main assumption. Correct answer is option D. Next question: what is the main advantage of biodrainage over conventional drainage system? So there are multiple options given. So we know that biodrainage. So biodrainage is like given is here. So in that we are growing certain trees and trees of having a higher root zone depth. So that basically absorb the water through root system. So along with this absorption, also absorb the salts and other part. So by absorbing this, it generally lower down the water because ultimately whatever what water is absorbing, it is moving or losing through the transpiration. So ultimately, it is removing water from the root zone. So in that, basically, we are growing trees like eucalyptus to extract the excess groundwater through transpiration. While other conventional drainage system like tile drain or mold drainage system, so that having limitation, uh, that is like limited capacity of water that draw and up to limited depth. So overall, the main advantages of biodrainage over conventional drainage system is there is use of plant energy to remove excess soil water via transpiration. There is no other energy required. Okay, so correct answer is option C. Question number 5. What is the key limitation of mold drainage compared to tile drainage? So mold drainage, we know that it is involves creating unlined circular channels in a heavy clay soil that have a clay content greater than 35% and sand content greater than 30%. And in sandy soil, channel walls collapse drastically and that reduce the drain life if you install mold drainage in sandy soil. And it is an economic alternative to pipe drains in a clay soil but unsuitable for permeable soil or steep gradient soil that have been graded more than 4%. In that case, we cannot do this kind of mold drainage. So rule of thumb is like depth to expanded to depth ratio is 1m7. It means if you have a 70 mm mold, then your depth must be around 490 mm depth. And typical spacing between mold drainage is 2 to 5 meter and its life is around 3 to 10 years depending on what kind of soil condition or design discharge you have. Now this key limitation of mold drainage compared to tile drainage is like requires high investment costs, cannot be applied in a high sand content soil, operates under deep water table condition. Yeah, it is correct. Then needs cemented or perforated pipes of flow conveyance. That is also correct. But like the second one, option B, that's have a major limitation, right, of this mold drainage system as compared to tiles. So it cannot be applied in a high like it cannot be applied in a high sand content soil, right? Correct answer is option B. Question number 6. The end drain model assumes steady state condition. So what is the primary implication of this assumption on the model result? So end drain models, we know that steady state flow, inflow, outflow, and hydraulic gradients remain constant throughout the time of the modeling, and there is no accumulation of water and energy storage in the system. So correct answer for this is like option Option B, where drain spacing and discharge remain constant over the time. Why? Because the computed drain spacing and discharge correspond with the equilibrium flow condition, often used for long-term drainage design and soil reclamation study. Right answer is option B. 7. In end-drain model, the assumption of two-dimensional vertical flow implies that two-dimensional vertical flow means that model domains is represented as vertical cross-section through the drain system. Okay, flow is analyzed in a horizontal as well as vertical direction. Sorry. Okay. And the third direction y along the length of drain is assumed to infinite and uniform. So there is a horizontal and vertical direction flow, and third direction that is along the length of pipe, right? Right. This direction. Suppose you installed this, so assume this is like 2D. That's why it is not visible. But like this pipe direction of along the pipe of land, that is uniform, and that is not much change. And this assumption simplifies the solution of flow equations and is valid when drainage is layout in a uniform and parallel. Drainage length is much greater than spacing, so lateral variation is negligible. Hence, the drain effectively models a series of repeating vertical slices, each representing the vertical or hydraulic behavior between adjacent drains. Correct answer is option C. Flow occurs only in vertical planes represent repeating along the drain length. Next question: which of the following features makes end drain superior to simple route equation in a complex field condition? So, we know that while route equation provides an analytical solution for drain spacing in homogeneous isotropic soils and multiple soil layers like up to three that allows in this model, and that also we can define multiple horizontal as well as vertical hydraulic conductivities, that is also called anisotropic, and flexible representation of hydraulic head distribution within the profile. This makes entrance particularly useful in heterogeneous soil, saline waterlogged areas, and reclaimed projects. So correct answer for this option B. So that allows the layered soil with anisotropy hydraulic conductivity. Now, question on the overall irrigation efficiency. So in this, generally we need to match with the correct one. So overall system efficiency, we know that overall system efficiency that is a product of reservoir, storage, conveyance, and application efficiency. Then your reservoir storage efficiency, so it measures the efficiency with which water is stored in reservoir. Conveyance efficiency, so conveyance efficiency is the ratio between whatever water that we have that reaches to the farm or what we have diverted. So, so its best match is option F. And your application efficiencies, application efficiencies are related to the ratio of volume of water stored in root zone and volume of water diverted to the field. And storage efficiency, so that is related to the field capacity of water. So like not a specifically defined in the context, typically involves reservoir storage efficiency. Okay. But like storage efficiency in general, that we know it is like more related to in context to field field storage efficiency. So it is related to whatever maximum field capacity of the soil and what is water that required to or as compared to current soil moisture content. Then you have a water distribution efficiency, that is more related to the ratio between mean numerical deviation from average depth to the water stored during irrigation. 7, that is Water use efficiency, so it measures the production of crop per unit water applied, like the rate in terms of transpiration, effective rainfall, or its both combined. Next question, which efficiency parameter is most useful for evaluating irrigation system at watershed or basin level? We know that at basin scale, water losses from one field may recharge groundwater or supply downstream users. Hence, effective irrigation efficiency consider the beneficial reuse of return flows, giving comprehensive picture of the water productivity and sustainability. So, correct answer is option C. Effective irrigation efficiency, that is very useful or most useful parameter for or just watershed or basin scale. And these are the like different values, typical ranges of each efficiency. Correct answer is option C. Next question, the overall irrigation efficiency of an irrigation project is given by. So overall efficiency, we know that is like multiplication of conveyance and application efficiency. There are 100, and it expresses how quickly water is delivered from source which is to stored in root zone of the crop. And its example, like if you have a conveyance efficiency 80%, application efficiency 70%. So how you can identify it overall? Just multiply it both and divide it by 100. So like overall application, overall irrigation efficiency is around 56%. You have a conveyance efficiency of 80% and application efficiency of 70%. Option B is correct. Question number 12. Which of the following losses is mainly affect the water conveyance efficiency? So you know that water conveyance efficiency includes the water that we have at farm, and whatever water we have diverted from source, its ratio is known as conveyance efficiency. And basically it includes the losses from the canal system or any supply system that using which we are diverting that water from source to the field. So like canal seepage and evaporation losses along the conveyance system. Option B is the best match. Question number 13, and the irrigation water application efficiency primarily depends on. So water application efficiency primarily depends on the soil moisture holding capacity and field leveling. So option A is the best match because you know that application efficiency is the ratio between whatever water stored in the root zone divided by water that is required for to bring it up to the field capacity. And this efficiency is totally depends on the field leveling, soil infiltration rate and texture, and irrigation methods. Next question, which of the following input modules in a crop plot essential only when irrigation scheduling is to be completed? So, soil module in a crop plot is required only when calculating irrigation scheduling because it defines field capacity, meeting point, and available water content. That will help us to decide when and how much to irrigate. While in contrast to other modules like crop or climate modules, so that help us to more detailed evaluation of different aspects of the project. But in case of when irrigation scheduling is required, that case soil module is uh, more decidable aspects. Option C is correct. The soil water storage efficiency represents soil storage efficiency. It is like water stored in root zone and water needed to bring to the field capacity. So that is your water storage efficiency. And in case of application efficiency, it is like water stored to the whatever water we have diverted to the field. That is your application efficiency. Storage efficiency. So sorry, I have to define like what to mention here because this is application efficiency is whatever water you stored in root zone to what amount of water you have diverted. Because there is always losses from runoff, evaporation, depopulation. So considering all this, you have application efficiency, but in case of storage efficiency, you have a ratio of water stored in root zone divided by water that is needed to bring it to the field capacity. So correct answer is option. Portion of applied water stored in root zone, effectiveness of replenishing soil moisture deficit, amount of rainfall contributed to irrigation, or total water lost due to absorption. Best match. Question number 16. Effective irrigation efficiency differs from overall irrigation efficiency because it ignores evaporation losses, accounts for beneficial reuse of drainage of populated water, includes rainfall only and depends only on crop efficiency. Correct answer is option B because we know that uh, in basin field study, like using effective irrigation efficiency is includes some water losses like depopulation, return flow, and that also can re-enter the groundwater recharge. And efficiency, effective efficiency that does include beneficial reused component as compared to overall irrigation efficiency. That is not included. Question number 17. Among the following irrigation methods, which typically has the highest water application efficiency? We know that water application efficiency is highest in case of drip irrigation system, then followed by sprinkler, then you have other surface irrigation system, depending on field condition and its design aspects. Correct answer is option D. The crop water require module CWR in crop water primarily calculates. So it is like for crop water requirement. So like you can say crop transpiration net irrigation requirement. So option B is the correct answer. Next question, the schedule module in a crop weight differs from scheme module because it, so you know that there is a schedule module as well as scheme module. So this schedule module simulates a field level irrigation scheduling using crop, soil and climatic data to determine when to irrigate, how much to irrigate and how soil moisture fluctuates over time. While scheme module in contrast operates at command area, okay, level and that calculates the aggregate water supply for multiple crops under given cropping pattern. So schedule that is generally for field level management and scheme is system level water planning. Okay. So schedule is which one is the best match? So calculate regional water supply based on crop pattern. Right. So schedule is more for option A. Determines daily and monthly irrigation timing and depth for single field. Okay, so this is regional. So no regional for regional there is a module called scheme we have, but for schedule field level management is better done by schedule module. So that determines daily, monthly, the seasonal water requirement, and that basically computes the timing and depth for water requirement for one field. Final answer is option B. Okay, so last question. Question number 20. When transferring crop weight result between two different climatic zones, the most critical adjustment required is, we know that most critical adjustment required is option B, that is crop coefficient and reference evapotranspiration, right? Because transferring irrigation scheduling across the climate requires normalizing crop coefficient with local reference evapotranspiration to maintain the realistic water demand estimations. Now, let's also look over at the numeric type of questions. So, question number one, overall irrigation efficiency of project is 48% and conveyance efficiency is 80%. So, what is the field application efficiency? We know that overall irrigation efficiency is defined as conveyance efficiency times application efficiency. So, just multiply, divide with 100. So, here we need to identify field application efficiency. So, here given is overall irrigation efficiency, that is 48%. Conveyance efficiency is 80%, and we need to identify EA. So EA is equal to E overall efficiency multiplied by 100 divided by conveyance efficiency. So overall efficiency we will get is 60%. Correct answer is option B. Question number two. Crop is grown in a soil having the soil moisture content at field capacity of 18%. The permissible soil moisture content depletion is 10%. Root zone depth of crop is 60 centimeter and crop over transpiration during crop period per month 30 days you can assume that is around 320 mm. There is no effective rainfall during crop season. It means there is no rainfall happening that are useful for plant. That there might be rainfall, but that is not effective and not useful for plant. The irrigation interval we need to identify considering this situation. So this So field capacity is given as 18%. Then permissible moisture content that like depletion allowed in this in the crop is around 10%. Then depth of root zone is 60 centimeter, and that nearly equal to 600 mm. Then P effective is 0, and ETC crop over transpiration during that 1 month is 320 mm. Now we know that to calculate the irrigation interval, first you have like what is the actual amount of water required by crop. So that is your 18% minus 10% moisture content. So that will give you a total water requirement divided multiply by depth of root zone. So that is your 60 mm or 600 mm, 60 centimeter, 600 mm. So that is your water requirement. And and what is the water required by crop? Okay, so this is your total water available capacity. Okay. Water storage capacity. This you have to apply what is requirement by crop. So that is your ETC divided by 30. So this is your daily water requirement. So once you do this irrigation interval calculation, your answer will come around 5 days. So that is nearly equal to 5 days. Now next question, if your 1.2 meter cube per second of water is diverted at the canal head and only 0.9 meter cube per second is what is the conveyance efficiency? You know that conveyance efficiency is the ratio of whatever water that is used to feed divided water you have 100. So your answer is 75. So this is the end of this lecture, and I hope you have enjoyed this entire series, and uh, this is helpful for your upcoming NPTEL examination. Yes, so with this, I'm ending this session here, and uh, yes, again, I'm requesting you to watch all the previous content that I've uploaded in this YouTube channel, and you can also access all the lecture materials through this Google Drive folder. And yeah, if you have any query, just write down to my provided email ID. I'm happy to answer. And best of for your upcoming NPTEL exam. And yeah, so thank you so much for joining this session. I may take one summary session uh, on Monday. So that also I'll summarize overall content to you. At that time, thank you so much, and good luck for your examination.